Very good morning to you all. Today we are going to see the compensation. Compensation means adding some zeros and poles to the original system to improve its performance, dynamic performance, to improve its dynamic performance. That is called compensation. Already we have seen proportional controller. That is one of the compensation. In that case, what we have seen is we are putting an amplifier in series with the original system. Amplifier whose gain is K in series with the original system. 1 upon G of S. This is called proportional compensation or proportional error compensation. Why it is called proportional error compensation means what is feedback C of S? What is error? Error at this point is R of S minus C of S. That is error E of S. So the error is given as input to this amplifier and it is amplified through this amplifier. In other words, the input to the system is, this is the input. Input to the system is, the input is here. The input to the system is amplification of error, or input to the system is proportional to error. Proportional to error. That's why it is called a proportional control. It's called a proportional control. What is steady state error for a type 0 system? E steady state equal to 1 upon 1 plus Kp, where Kp equal to position error. Position error. The steady state error for step input, that is position error, is 1 by 1 plus Kp. Kp equal to limit S tends to 0, G of S. That is equal to, what is system? System is K multiplied by G of S, where G is the, K is the amplifier. Because these two are cascaded, we know that if two blocks are cascaded, we can multiply. That's why we multiply that K with that G. So if we take, is a type 0 system, that's why what we will get is Kp equal to K. Therefore, E steady state equal to 1 by 1 plus K. As K increases, steady state error will decrease. As K increases, steady state error will decrease. That we know. For what value of K, the steady state error will become 0. For infinity, the steady state error will become 0. That's why we cannot make that gain equal to infinity. It is not possible. It is not possible to make gain equal to infinity. That is one thing. Therefore, even if we have a compensator, proportional compensator, it's not possible to remove steady state error. Not possible to remove steady state error, because it's not possible to make gain equal to infinity. If we make infinity, then only for a type 0 system, the error will become 0. It's not possible to make infinity. That's why it is not possible to remove steady state error by simply using that gain. But we can reduce the steady state error. As K increases, the steady state error decreases. Another problem with K is, the second problem is, from third order onwards, third order system onwards, if K increases, the poles will move. The poles will move towards RHP. It will move towards RHP. It will move towards RHP. That's why we know that suppose I am having a open loop transfer function K GS. If you find the closed loop transfer function G compensated system equal to KGS. What is the closed loop transfer function? KGS upon 1 plus KGS H of S. But for a unity feedback system, H of S equal to 1. Suppose G of S equal to 1 upon S multiplied by S plus 1. Let us assume S square. Sorry, S square S plus 1, third order. Okay, S cube plus S square. So let us assume that G of S equal to 1 upon S cube plus S square plus S. Let us assume. In that case, if you replace the G of S by this, what you will get? The closed loop transfer function T of S equal to K upon S cube plus S square plus S plus K. So the denominator becomes function of K. The denominator becomes, if you find a closed loop transfer function, in place of G of S, we substituted 1 upon S cube plus S square plus S. If you substitute that, what you will get is K upon S cube plus S square plus S plus K you will get. Here, the K is part of denominator. But where we included the K, we included in the forward part, that too in the numerator. But in the closed loop, it becomes part of denominator. That's why the poles will be varying as K varies. From third order onwards, suppose I'm having a third order system like this. I'm having poles like this for a third order system means if you increase K, this is when K equal to 0. If you increase K, what will happen? This pole will move towards left-hand side, but these two poles will move towards right-hand side. This pole also will move towards right-hand side as K increases. It means 2 of the poles are moving towards the right-hand side. As K increases, it will go to the right-hand side. That's why you cannot increase K beyond a certain value to remove steady-state error. That is the second point. So these are the drawbacks with amplifier gain. That is proportional controller, proportional compensation. And the drawbacks with the proportional compensation. The first point is not possible to remove steady-state error. Because for a type 0 system, as K tends to infinity, then only the steady-state error becomes 0. The steady-state error becomes 0. But it's not possible to have an amplifier with infinite gain. That is first point. That's why always steady-state error will be there, even if you put this controller. That is first point. The second one is from third order onwards, if we increase K, the closed loop poles will move towards right-hand side. That's why after certain value of K, the system becomes unstable. You cannot increase the maximum value of K is called K max. Up to K max only you can increase the gain of the amplifier. If you increase further, it becomes unstable. So these are the two drawbacks. Now, these are the two drawbacks with the proportional compensation or proportional error compensation, or simply called the proportional controller. Now let us see derivative error compensation.